Wolfgang Pauli, came along to the scene and they started putting all the quantum numbers together. And he came out, long story short, with an idea called the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons in the same atom can have the same set of 4 quantum numbers. So what this means is that when you're putting electrons around atoms, each electron has to have its own set of quantum numbers. And I use the idea of an address. If I wanted to invite Joe but not Bill to my party, all right, I could know Joe's address. I don't have to send an invitation to Bill. All right, that's kind of sad. I apologize, Bill. But anyway, you get the idea. Each electron has to have its own address too. So if you want electron number 7 to come, but not electron number 9 to your party, then in theory you could use the 4 quantum numbers to distinguish electron 7 from electron 9. It's pretty clever what he came up with. Let's look at some examples of this. Now, in Chapter 6, Part 1, we looked at n, l, and m sub l. And when n equals 1, l, which can be no bigger than n minus 1, has to be 0. And m sub l depends on l, negative l to positive l. So if l is 0, m sub l can only be 0. And we saw how when n equals 1, l equals 0, this is a 1s orbital, all right, because n is 1. When l is 0, you have s. That's the stupid people driving freaking gas hogs, or whichever version you want to use. So if you can have only 2 electrons in each orbital, the 1s is an orbital. And so we can actually assign now the 4 quantum numbers. And for electrons in the 1s orbital, you can have n equals 1, l equals 0, m sub l equals 0, and m sub s equals 1/2. And you can have n equals 1, l equals 0, m sub l equals 0, m sub l equals minus 1/2. So the first set of quantum numbers was electron number 1's address. The second set of quantum numbers was electron number 2's address. And again, Pauli exclusion principle just says that each electron has to have its own set of 4 quantum numbers. So as long as we don't have any more electrons with those exact quantum numbers, we are good to go. So what you've just done there is you have figured out the electrons in the quote-unquote 1s2 filled electron shell. If that means something to you, cool. And if it doesn't, don't worry, we'll talk about that in a little bit. But again, what we're doing is we're putting individual electrons in the orbitals, and we're seeing how they worked out. So the s orbital, we're going to see, can only hold 2 electrons. When n equals 2, we saw that L can be 0 or 1. L goes from 0 up to n minus 1. 2 minus 1 means a maximum of 1. So there are 2 subshells on the n equals 2 shell. And again, it's like 2 houses on the n equals 2 street, while on the n equals 1 street, there was only 1 subshell, 1 house. But anyway, I digress. Now, the lower right-hand corner there, it has the different electrons possible and their quantum numbers for the 8 electrons that goes inside. So let's look at the first 2 right here first, all right? Those are n equals 2, L equals 0, M sub L equals 0. When L equals 0, M sub L can only equal 0, so there's only one allowed M sub L. And like before, M sub S can be positive 1/2 or negative 1/2. So these first 2 electrons are the 2 electrons going to go in the 2s orbital, or the 2s subshell, if you will. The next ones now are when we start playing with L equals 1. Now when L equals 1, M sub L goes from negative L to positive L. So that means negative 1, 0, and plus 1. Now up until this point, we've only had one value of M sub L, and M sub S could be positive, negative 1/2. But now we have 3 M sub L values, negative 1, 0, and plus 1. And these kind of correspond to the X, Y, and Z axis, like we saw in Chapter 6, Part 1. But anyway, each of those M sub L's can have two possible m sub s values. So you can see the first two there are the two electrons going in when m sub l equals -1. The next two are for when m sub l equals 0, and the last two are for when m sub l equals +1. This type of orbital is the 2p. Remember, when L equals 1, that's p. When L equals 0, that's s. L equals 2 is d, etc., etc. So what this means is if you count these electrons up, there are 6 electrons in the 2p orbitals. You could also say that the 2p subshell holds 6 electrons. Each of the m sub l values is a subshell, or an orbital, excuse me. So there are 3 orbitals, 2 electrons per orbital because of the m sub s, total of 6 electrons in the 2p subshell. So for the n equals 2 shell, you've got 2 electrons in the 2s, 6 electrons in the 2p, 8 electrons total. And again, we're giving each electron its own set of quantum numbers, which is kind of cool. Oh, but there's more. When n equals 3, we start getting into the 3D systems. But like before, when n equals 3, L goes from 0 up to n-1, so 0, 1, and 2. And like before, there's a 3S system when L equals 0. There's a 3P system when L equals 1. But now we have a 3D when L equals 2. And as before, we can break all those quantum numbers down. Here are the two 3s electrons. Right to there represents the 6 3p electrons. And then finally, you've got the 10 3d electrons. Notice the patterns. Quantum chemistry and quantum physics is just filled with patterns. 2 electrons per s orbital, 6 electrons per p, 10 electrons per d. Notice there's a gap of 4 electrons between those numbers. We're going to see this pattern continued. When all is said and done, the n equals 3 shell is going to have 3 subshells, the 3s, 3p, and 3d. The 3s subshell has 1 orbital for 2 electrons. The 3p subshell has 3 orbitals for 6 electrons. And the 3d subshell has 5 orbitals for 10 electrons. There are 18 electrons total in the n equals 3. Oh, but you can keep going. Here's n equals 4. When n equals 4, L goes to 0, 1, 2, and 3. Remember, you go up to n-1. So now we have an F player. And again, like before, 2, 6, 10 for the S, P, and D. And you guessed it, the F, the next one will have 4 more than the D. So it's going to have 14 electrons total. So again, like before, here's all these different pieces. All right, here's the 4S. To number 8 is the 4p. The rest of them in that column there are 4d, and now in the lower right, 4f. And you can keep going and going and going. But nowhere in all of these slides we've seen have the quantum numbers been repeated. And that's the idea behind Pauli exclusion principle. You have to have each electron have its own set of quantum numbers. We're going to do it this way, which is really cool. Now, on a practical level, notice here how all of the S systems, whether it's 1s, 2s, 3s, etc., they've all held 2 electrons. And the p system, the p subshells, because of their 3 orbitals, have always hold 6 electrons. And the d's hold up to 10, and the f's hold up to 14. This will help us later on. This is an overview of some of the things that are possible. The left-hand side shows the electron shells, 1, 2, 3, 4. And again, we went up to just 4 and stuff like that, but you could keep going. Then it shows the letters associated with them. Notice that there's a G for 5 and even an H for 6. There's also stars next to them. We haven't really seen those yet and stuff, but maybe one day. Anyway, then it says total number of orbitals available. If you have the L value, the number of orbitals equals 2L plus 1. If you have just the shell number, the n squared value will tell you the number of orbitals. Number of electrons, maximum electrons per the shell. And here's another little shortcut. 2n squared is going to equal the number of electrons for the shell. So there's different kind of things here and stuff, and figuring out how these work is part of your goal for this section. It's not hard. It's also kind of cool to remember that we're looking at the results of some calculus calculations here. And it's a little bit strange, but it is arguably easier than the actual math used to figure out these quantum numbers for electrons, stuff like that. Whoa, kind of trippy.